So now we will look at magnetic flux and how this gives rise to the Faraday's law. Faraday's law. And this is sort of, I'm going to put in parentheses here. We use this to figure out how to generate electricity. So I'm going to put here generation of electricity, generation of electricity by using the magnetic fields. So you can produce electricity with magnetic fields, and let's see if we can make sense out of it. So from experiments, it can be shown that the voltage, so here's a picture. First, let's look at the picture here. You have a loop. Here's the loop. It's a loop of a conducting wire, and this loop sits in a magnetic field, and you can easily calculate the flux of the magnetic field. Now, if that flux changes, then that is going to induce a voltage in that loop. And we can write it in the following way. Voltage, I'm going to put here, let me actually put something here. So voltage is going to be EMF. And the equation, Faraday's law equation, is that EMF or voltage is equal to the change, there should be a negative sign, I think here, yeah. Negative, the change of the flux with time, change of the magnetic flux with time. So if there's a changing magnetic flux through the loop, then you will have a current flowing along this loop. Now that should make sense, and it should make sense for the following reason. Suppose you have, let's draw a few things on that picture over there that we have to the right. Actually, let's keep that picture as it is, because I kind of need it for the problem that I'm going to solve here. So let's maybe redraw it. What we have is here's a loop. The loop looks like this. And then here's the vector A that points out of it. I guess I'll just draw a small one. So here's vector A. Right, and that's perpendicular to the surface of the loop. Okay, the loop itself is made out of a conductive substance, conductive material. And so what we have here is a bunch of positive charges all over the place. In fact, it's the electrons that move, but, you know, whatever, we consider the movement of positive charges in terms of a conventional current. So you have a bunch of charges that sit here in this wire, because this wire is made out of atoms, and within atoms you have positive charges. So I'm going to put a bunch of positives all over the place along this wire. Now we have the magnetic field that is pointing through this thing to the right, and of course this magnetic field is not just pointing at the center of the loop, through the center of the loop, but it is everywhere. So I also have the magnetic field out here. I also have the magnetic field here, and I also have the magnetic field on the bottom, and I have the magnetic field on the top as well, right? So there's magnetic field all over the place. Let's maybe draw a few more. So here's the magnetic field. I'll draw one more over here. I'm gonna put one more over there. And then at the bottom, likewise, here I have the magnetic field that points like this, and then over there I have magnetic field, and here I have magnetic field. There's magnetic field everywhere through this whole page. Now I'm going to get rid of all of these. Actually, let's keep them there. If this magnetic field is not changing at all, then there's going to be no force on these charges. But if this magnetic field changes in some way, then that's as if you were moving the wire around. And if you move the wire around, then you're pushing charges through the magnetic field, and there's going to be force. Actually, maybe I should start with that. Suppose you take this loop and you just move it around. So you take this loop and you move it all over the place. Well, when you do that, what you're doing is you're pushing charges through the magnetic field. And if you push charges through the magnetic field, there's going to be a force on them. So you should suspect that if this loop moves in some way, then the charges can flow. Right? Now, the movement, turns out, actually has to be such that the flux has to change. And if you can do that, then the charges will actually flow. The forces will work in such a way on these little charges that the charges will actually flow. And so all of it amounts to the following. Changing magnetic flux will imply that you have some kind of a voltage here, or induced voltage in the loop such that the charges can actually flow. All right, we should probably spend more time on this. The equation is simple. I mean, it's just the change of the flux over the change of time gives you the voltage. But let's try to spend more time on this concept here. So suppose that you have a magnetic field that points into the page. So let's draw it here. Here's a magnetic field that points into the page. And then let's say that you have a loop, but we're going to take a square loop and we're going to set it up right here. So here's the loop. And then we're going to take this loop and we will move it into the magnetic field. So at this point, I have no flux through the loop, no flux through the loop. At this point, the flux through the loop is increasing, the flux is increasing, the flux is increasing. That would imply that I had some voltage in the loop and therefore the current flew. Now, as I move this loop in this field here, there is no change of the flux. It's the same flux through this loop, magnetic field times A. And so there's no change of flux, therefore there's no voltage, therefore no current flows. And then as I slide this loop out of the magnetic field, the flux is decreasing, and if the flux is decreasing, then it's changing, therefore there's voltage there. And then I have no flux, the flux is 0, and there's no changing flux, therefore I have no voltage. All right, so let's go back. It's obvious that I don't have any flow of charges in this case, right? But as I move this to the right, right here. So let's consider this case. Let's give it a velocity v to the right. So let's say that this loop moves to the right at speed v. Now let's consider the right-hand rule and see how the right-hand rule gives us the direction of the forces on the charges here. So you have positives along this wire simply because you have atoms there. So there are charges in these 4 sections. And as you move these charges, drag these charges through the magnetic field, they will experience a force. So let's consider a force on these charges here first. Use the right-hand rule. I'm going to put here on top, use the right-hand rule and determine the direction of the force. Well, the magnetic field points into the page. So you take the fingers of your right hand, make them point into the screen. V points to the right, therefore the force comes out of the palm of your hand. So here's the force. The force just points up. Force on these charges points up. There's going to be a force on these charges upwards. And perhaps they can move actually upwards. Well, anyways, let's consider here this section. So there's no magnetic field here yet, so there's no force on these charges. They just sort of sit there. There's no force on them. And so the force here, I'm going to write that the force here is 0, while this loop is moving into the magnetic field. Now the charge is on top here. So this charge, there's no force on it because it's not yet in a magnetic field. This charge, there's no force on it because it's not yet in a magnetic field. But this charge here, it is already in a magnetic field and it moves to the right. So let's see how that goes. The force on this charge would be up, right? The force here would be up. So I'm going to put here force is pointing up. And then let's consider at the bottom here. Force on this charge is 0 because it's not yet in a magnetic field. Force on this charge is 0. It's not yet in a magnetic field. Force on this charge is up. So the force acting on this charge in the upward direction is going to make this charge go nowhere because the charge cannot jump off the wire. Same thing here. The force pushing at this charge upwards is going to make this charge go nowhere because the charge cannot jump off the wire. But this force here pushes the charges upwards, and so they will move up because they can. And I'm going to end up here with a current that flows in the following direction. So there's going to be a current here that flows like this, I. Same thing happens when I'm pulling this, okay, well, so let's clean this up a little. Let's get rid of the B. That's going to be in my way. Let's extend this magnetic field so that we consider this, what we need is blue. Let's make this magnetic field longer. And now let's take this whole loop and let's place this loop here. Here's the loop. And then this loop is moving at velocity v to the right, but now this loop is entirely in the magnetic field. So this loop is entirely in the magnetic field, and it is moving through this magnetic field at speed v. We still have the charges all over the place here in this wire, right? We have charges there because you have atoms there, and so we have these positive charges. And let's consider the forces. Well, the forces on these charges here, as they move through the magnetic field to the right, would be the force here would point up. The force on this one would point up. The force on this one would point up. The force on this one would also point up, but they can't jump off the wire, so these forces here are insignificant. The force here would point up, the force here would point up, and the force here would point up. But again, these forces can't make these charges jump into the air, and so this force is insignificant. And then the force here on these charges, well, the charges move to the right, and therefore the forces on these would also be up. And so now what I have is, let's call this F1, let's call this thing F2. F2 and F1 would have the same magnitude but opposite, therefore this push would cancel this push, and so there would be no flow. So in the middle here, you would have no current I. So if you take this loop and you drag it anywhere you want to here within this magnetic field, such that the magnetic field through the loop doesn't change, right? There's no changing flux here in this case as you drag this loop all over the place, then there's going to be no flow of charges. Versus here, the force on this section of the wire is going to induce a current, but that is only because there's no force on this side. And in this case here, in red, flux is increasing. Flux is increasing. In this case here, flux is constant. And now let's consider one more case where we take this loop and we drag it out of the magnetic field. So here's the loop, it moves to the right at speed v. And again, we have charges all over the place. So let's put charges all over the place. We have these positives. And let's consider the forces. So forces on these three charges here, well, this force is 0 because these charges are no longer in the magnetic field. The force on this one is 0 because it's not in the magnetic field. The force on this one is 0 because it's not in the magnetic field. The force on this one is up. The force on these three charges would also be up. Here's force F. And then the force on this charge would be up. And then the force on these here would be 0 because they're not in the magnetic field. Now, this force is insignificant because it's not going to make this charge jump into the air. This force is insignificant. It won't make this charge jump into the air. But this force is significant, and there's no force to counterbalance it on the other side. Therefore, I'm going to end up with a current here that flows like this. And note that in this case, I have a changing flux. In fact, here flux of the magnetic field is decreasing. Now, changing flux gives me a voltage, induced voltage in the loop, and that comes from the right-hand rule, if you will, but that gives rise to the current I. Likewise here, changing flux gives me voltage, comes from the right-hand rule, and that voltage and the force there, they will give me I. So as long as you have changing flux, you will have voltage. But if you do not have a changing flux, such as in this case, you won't have any voltage. And so this is basically what this Faraday's law is saying. Go back here. This is the Faraday's law. What it says is that if you have a changing magnetic flux through a loop, then you will have a voltage in that loop, or EMF is what we call it. Okay, so that was the concept. That was sort of a conceptual justification of the equation. The equation itself comes out of the experiment. And now let's do a sample problem. So I'm going to solve number 1 that I have here. It's also number 1 on your worksheet. So let's set this up. Here's number 1, and let's see what it says. Circular loop of a conducting wire of radius r equals 15 centimeters. So I have the radius being 1.15 meters. That of course will give me the area of the loop. Area is pi r squared. So let's calculate this. So this is 0.07 meters squared. So that's the area of the loop. Placed in a uniform magnetic field. And what else do I have? The direction of the magnetic field makes an angle of 30 degrees with respect to the area of the loop. All right, let's draw it. So what I have is, let me draw it like this. Now, we do have this picture here on top, so we can refer to this picture here. But I'm going to draw it like this. Here's the magnetic field, and let's say that the magnetic field points to the right. And this magnetic field will change. So there's going to be some initial magnetic field, and that is 1 Tesla. It increases at a constant rate from 1 to 5. So this is 1 Tesla. And then the final magnetic field is 5 Tesla. So there's an increase in the magnetic field. But I have a loop here in this whole thing, and I'm going to set up the loop. I'm going to draw the loop like this. Here's a dot, so that the loop comes out of the page, and then it goes this way, goes into the page on the bottom. I actually don't want to put the loop, I mean this circle there on top, because that it kind of indicates the direction of the current, and we're not playing with the direction of the current yet. So I'm just going to draw the loop like this. So what I have is that the wire comes out of the page here on the top, goes down, and then at the bottom goes into the page, and then loops around. So I guess I'll put a little X, but I'm not referring here to the direction of the current. All right, so the wire comes out of the page on the top, goes down and goes into the page, and then comes back up again. So why did I do that? Well, I did that because when you look at the text here, it says right here, the direction of the magnetic field makes an angle of 30 degrees with respect to the area of the loop. That's not very clear what it actually means. So I'm going to draw here A like this. Here's vector A, and I have A. I know what A is. It's at 90 degrees here to that, and A is 0.07 meters squared. Now, what angle is it exactly that is meant there by that? Is it this angle, the 30 degrees? Is it this angle here, or is it the other angle? It's hard to tell from the text. So let's say that this is the angle that it actually gives me. Let's say that this is the angle that the problem gives me, and then I'll take it from here. What I do need, though, is not, if this is in fact the angle that the problem gives me, then that's not what I need. What I need is this. This is the angle theta that I need. And so let's go ahead and see, I think I have, the time in which this thing changes. So I have the magnetic field here, goes from 1 Tesla to 5 Teslas. This change takes place in a time of 10 seconds. So this takes place in a time of 10 seconds. And what's also given to me is the resistance of the loop. So I have the resistance of the loop as 15 ohms. All right, so this is the setup. And the question is, what is the voltage generated around the loop, and what is the current? So let's state the unknowns. Unknowns are the voltage, or EMF is the unknown, and the current in a loop. Right, so sort of try to understand this. What we have is a loop that sits in the magnetic field, and then we increase the size or the magnitude of the magnetic field. By increasing the magnetic field value here, we're going to generate a force on the charges in the loop, and the charges will flow. So anyway, let's go ahead and calculate that. So the EMF is minus change of the flux over the time, and so of course this is just minus 1/10 times, we have 10 seconds for the change here, times the change of the magnetic flux, and magnetic flux is A times B times the cosine of the angle theta. And you have to now look at which thing is changing here. Is it the area that is changing? Is it B, magnetic field, that is changing? Or is it the angle between A and B that are changing? Well, area of the loop is not changing. The angle between A and B is not changing. The only thing that changes here is B. And so this equation becomes epsilon equals minus 1 over 10 times A times the cosine of theta times delta B. So I have minus 1/10 times 0.07 times the cosine of, and the angle here would be 60, times the cosine of 60 times the change of the magnetic field, so 5 minus 1, right? This angle here is 60 degrees because 90 minus 30 is 60. And so the EMF or the voltage setup would be minus, let's calculate this thing out. So it's 0.014 volts. Don't worry about what the negative means here in this expression or in this equation. It has its significance, but we'll get back to that with Lenz's law later on. So for the moment, just keep the negative, but don't worry about it. All right, so you figured out the voltage that is present in this loop. That's as if you had a battery there and that battery was pushing the charges, but it's not actually the battery. It's rather the changing magnetic field that generates this push on the charges. I can also calculate the current because current is delta V over R. And so I have here a point, keep the negative, but don't worry about it, negative 0.014 divided by the resistance, which was 15, and that gives me almost 0.01 amps, and we could leave it there. All right, so the last concept for the Faraday's law is that, so sure, that's true, but that's true if you only have one single loop. And in this specific picture here, you have one single loop. Well, what if you had a coil? That is, what if this wire continued on? And so you had another loop here. See if I can draw it, another loop and another loop and another loop. And it's not like you had separate loops, but you had one wire that was just sort of coiled into this solenoid. So what if you had a solenoid instead, where you had n number of loops? Here's n number of loops that you have in this picture. Well, in that case, turns out that you just take the flux, changing flux, and you multiply it by n. So if this problem here said that there were 100 loops in the solenoid, then in that case, instead of having one loop here, you would have 100 loops, and this would be a solenoid. So the wire, it's one wire that loops around. You would have to take this voltage here, EMF, and you'd have to write negative 0.014 times 100, and now you would get negative 1.4 volts. So the more loops you have in your solenoid, if this is solenoid, the more loops you have in your solenoid, the bigger the voltage that you can generate. And what that gives us is sort of the following concept: that if you have a magnetic field and the magnetic field points in this direction, so perhaps you would have a some kind of a setup here where you have a magnet with a north pole and then a magnet here with a south pole. And then you place a solenoid on the inside here, so that you have a solenoid that does something like this. All right, so here's your solenoid where a vector points like that at the moment. And then if you could mount this thing, well, I don't know, we didn't quite yet get there, I suppose, but what you could do is this would be a weird way to generate electricity, but what you could do is you could take this magnet and you could move it away and then move it back in. And as you move it away and back in, away and back in, you're varying the size of the magnetic field B. And as you vary the size of the magnetic field B, there's a changing flux through this solenoid, and the changing flux through this solenoid is going to give you rise to some EMF or voltage that would be set up in this solenoid. And if that's true, then you would have some charge flowing. You would have some current flowing in this loop. So you could generate electricity this way if you wanted to. It's not the most efficient way actually, but we're getting there. Almost ready to look at the typical way we generate electricity.